So the okay, so we're discussing, we're embarking on proof of this theorem, which controls the growth of the support of the vorticity for the Euler equations with the background flow. We start with vorticity contained in the ball radius epsilon, and this will tell us that it remains contained in the ball radius a little bit bigger than the square root of epsilon for arbitrarily long times if epsilon is small enough. Okay, and so what we're doing is this. I mean, so I have some. So the main point will be I have some function chi tilde who looks like this. In fact, it'll go from R to 2R. It will look like 0 here and 1 out here, and then in between is smooth. And so I multiply the vorticity by this weight, and so this is essentially looking at the amount of vorticity outside a ball of radius capital R. And I'd like to control the growth in time of that quantity. And I'd like to be able to do this for a range of R's. And so eventually when I do this, which will start later today, I think, I'll just differentiate this in time and I'll get a bunch of terms that will appear. And so what I've been doing is essentially estimating the terms that arise when I do this computation, when I compute d dt of this thing. And so that's the program. And so what we've done so far is we've started, I guess I proved these first two lemmas and I stated the third one. And so the first lemma in some ways is the reason why we need p larger than 2 in these in this proof. So anyway, these are the statements. Let's not repeat them. And then I owe you a proof of the third lemma. And so, okay, so let me just remark, when I do this computation, I'll get terms involving the gradient of chi multiplied by dp dt, and I'll get terms involving the gradient of time multiplied by the velocity field u, and then I can rewrite that using the Biot-Savart kernel. And I'll get things involving the gradient of phi multiplied by, also the background flow f will appear. And so somehow this last lemma will address terms involving the background flow, and the middle lemma involves the velocity field u generated by the vorticity. We can see this is basically the Biot-Savart kernel. Okay, so let's prove lemma 3. And okay, so this should be easy. So let's let R be the norm of x. And let me write, so f of x minus this integral, f of y omega epsilon of y over capital omega dy. This is integral over R2. Well, first thing I can do is I can rewrite this because I'll rewrite this as follows. Right, so the integral of omega, little omega over capital omega is 1. So I can bring this inside here. And I'll write this as the integral over the ball radius R. R being, again, the modulus of x. I'm going to stop writing subscripts. Well, I'll write them for a little longer. And then the integral over the complement. Okay, and let's see, what should we do? For the first one, so if I then look at the modulus, the absolute value of the integral, so the first one, well, let's see, it's less than the Lipschitz constant times x minus y times omega epsilon of, let's see, is this what I want? Yeah, this looks okay. And then, and the Lipschitz constant is this. And then the second term, I'll just multiply, I'll just estimate this fx minus fy by 2 times the L infinity norm of f times the integral over the complement of omega dy. And what I can do here is I can multiply this, I can insert in here something that's bigger than 1. And so let me insert y squared over r squared. That's always bigger than 1 on the complement of the ball radius r. And okay, good. And so then this is, so in the ball radius r, this is less than the Lipschitz constant times 2r times the integral, which is 1. And, well, okay, let's write this. And maybe I have a 4, if I put a 2 here and a 4 there, for f infinity over r squared times the second moment. Okay, and I'm always happy when I see a second moment because my assumption is that this is order epsilon squared, the integral of y squared omega of y dy is this small. And let's see, that's what we had up here. So that's good to remember that r is the norm of x. Okay, easy to find that. Okay, so now here's one of the main points, and actually we've so I've broken things into little pieces because we'll want to quote some of the ingredients again and again, and so this has the feature or the bug, depending on how you feel, that from now on every lemma will be some sort of easy calculations, and then we say, well, then we appeal to what we've done before. Okay, so here's the next lemma, and this is sort of a crucial one. Okay, so here I assume G is a Lipschitz continuous vector field. It vanishes in the ball radius r around the origin. And G is always orthogonal to G is always a, this is G as a radial, G points radially outward. So G of X is this is what the second assumption says. So I can always express G as a component, a radial component, and a rotational component, an angular component, and the angular component vanishes. Okay, and so in practice, G is going to be the gradient of a function who depends only on the distance from the origin, and so that would be a radial vector. Okay, as usual, I define P epsilon to be the center of vorticity of some omega epsilon, and omega epsilon has the same characters, doesn't change sign, etc. Its integral is capital omega, and so we have this estimate which is a bit opaque. And so again, the point is this is the kind of term that will appear in when we try to control the growth in time of the amount of vorticity outside a certain ball. And the point is that this is some kind of a, because of this assumption about G, this is some sort of outward radial velocity. So this x minus y perp times omega of y dy, that integral, is the velocity generated by the vorticity field, by the vorticity omega up to the constant. This is the and so there's some kind of weighted radial, some sort of weighting of the radial outward velocity. That's what we're estimating here. And so it's controlled by, well, we have, okay, norms of G, natural enough. So this ball, this radius R appears, the radius of the ball in which G vanishes. And not surprisingly, we expect, so if it vanishes on a smaller ball, that's then, so here we're looking at the distance from the center vortex. If it vanishes on a smaller ball, that's not more dangerous. It's getting closer to the singularity of the BSR kernel. And then what do we have here? Here we have the second moment. I like that. That's always over epsilon. And then this M of R is the amount of vorticity outside. So here's the definition of M. M is the amount of vorticity outside a ball of radius R in the plane. And so again, if R is big, I expect this should be getting small. And so this is the lemma I hope to prove. And we'll see this is sort of a main point in the eventual proof of the theorem. Okay, so I've recorded up here the earlier lemma. And so here's the proof. Okay, so first, I can assume the center of vorticity is 0 by translation. We've done this before. And so, so I assume this is 0 and then this is no longer here. Okay, and then I'm trying to estimate this. And so one thing I can do is, well, let's write it. The thing I want to estimate is G of X dot X minus Y orthogonal over X minus Y squared omega X omega of Y dx dy. So I'm not writing subscript omega both because if I do, it'll just be this illegible scroll. What is this? And so this is, so the first thing I'll do is a trick similar to something we've done already. And so I claim that by anti-symmetry of the Biot of R kernel, I can write this as G of X minus G of Y, the dot product with X minus Y orthogonal over X minus Y squared omega of X omega of Y dx dy. Because look, if in this expression, if I just change the roles of X and Y, that all that does is it introduces a minus sign because of the odd character of this BSR kernel. And so I change the role of X and Y. I get the same with minus sign, take the average of those two expressions. Okay, and so let me call this, let me first bring this inside, it doesn't matter. Let me call this f of X and Y. Okay, and so this is the integral over, I should have made it clear, R2 cross R2. And so note, G is 0 and the ball radius R. So f of X and Y is 0 if both X and Y belong to the ball radius R. And so I'm integrating only over points who are some distance away from the origin. And let me see. So then let's call this A. And so then A I can write as, well, I'll write as the integral where X is a distance greater than R from the origin. Let's see. Let's call it maybe S So S is, well, is just the complement of the ball radius R. Okay, so it's this, and then the integral over R2 cross S. And so here, this is the case when, so here X is bigger than R, here Y is bigger than R. And I've counted the region where both points are bigger than R. I've counted that twice. Okay, so that's this. And then if I look at this definition of F up here, it's symmetric with respect to X and Y. And so these two terms are equal. The first two terms are equal. Okay, and then let me again break the first term into two pieces. And so there'll be a piece that's S and say the ball of radius R over 2. So S is the, well, okay, we don't know what it is. It's the complement of the ball of radius R. And then S and the ball of radius R over 2 complement. And then we have a S cross S. And in every case, we're integrating this integrand, f of xy dx dy. Okay, and so so in the first case, so here's the situation. I have control. I have good control over the this I of omega, which is up here someplace. Well, where is it? Well, okay, so I want to assume that this is order epsilon squared. And this involves the vorticity multiplied by a weight of x squared. And so this gives us good control. It gives us lousy control if I'm too close to the center of vorticity. And away from center of vorticity, this is pretty helpful. And so, okay, and so I've split the integral into one dangerous piece where I have, so for this piece, I have some contributions where I'm looking at points near the center of vorticity. That's a bit dangerous. But the good thing is that in those, that for y's near the center of vorticity, they're paired with x's who are farther from the center of vorticity and also bounded some distance away from them. And so that prevents the BOSR kernel from blowing up. And then the other piece is everything's far from the center of vorticity. I don't have to worry. I can estimate that easily using this control over this second moment. Okay, so that's the plan. And let's call this, say, A1 plus A2 plus A3. And so then in A1, so remember, we're integrating, so f of xy is g of x minus g of y, the dot product of the BOSR kernel. And in A1, this g of y is equal to 0. Omega, and this equals 0. And so, so let's see, what do we have? And then And here's where I'll use my, my assumption about the form of G from above. So A1 is equal to, so we only have the terms involving G of X, and we write that as G of X, the radial component, times a radial vector. And then, so this is the integral over, say, S, and then here I have the integral over a ball of radius R over 2. This is the Y integral. X minus Y orthogonal over X minus Y squared omega of Y dy. And then I guess I have an omega of X dx. Okay, and but this is exactly the quantity from the earlier lemma, right? So so if we assume P is 0, then we have exactly this quantity where what? So here here H is R over 2, right? And so I have so here, remember, okay, actually H is okay, so X is actually the modulus of X is bigger than, is greater than R, but we can apply this with H equals R over 2. And okay, so and so then we find, I believe, that we say this is bounded by well, constant times over R cubed times this I of omega epsilon. So this was the hardest of the lemmas we proved on Monday, where we, what did we do? We again did some kind of we had this x dot x minus y perp. We wrote that as x dot y perp. We again sort of anti-symmetrized to have x minus y dot y minus x. And the key point was that we added and subtracted a term using the definition center vorticity to manufacture some cancellation to get a term involving 1 over x minus y squared minus 1 over x squared. And that got us some cancellation that allowed us to obtain this conclusion. Okay, so that's this. And then, right. And so we see rather easily that this is bounded by, well, this is just bounded by the L-infinity norm. Okay, and moreover, well, constant over R cubed, this second moment. And then also, when I look at the integral over S, this is supported outside the ball. This is outside the ball radius R, and so so this will only pick up the vorticity outside the ball radius R, which I called, I guess, M of R. Okay, and is that the lemma? No, that's only one piece of the lemma. So we split this into several pieces, and we've taken care of this one. And then for the other two pieces, I claim let's look back up here. Right, so I always want estimates involving this M of R times the second moment, so the vorticity outside a ball times the second moment, and then multiplied by things who depend on negative powers of this R. And so we've got the G infinity, the L infinity norm over R cubed. And So for the other ones, but these will be easy because we're away from the center of vorticity where this I of omega is pretty helpful. Okay, so the claim is that the integral over S cross the ball of radius R over 2 complement of this f of xy dx dy is bounded by the Lipschitz norm over R squared times the vorticity outside the ball radius R times the second moment. Okay, and so this will finish the proof. Since both A1 and A2 are bounded by an absolute value, are bounded by this integral. So remember, A1 and A2 were integrals without absolute values of just this quantity over different subsets of points where both x and y are bounded away from the center of vorticity. Okay, and so the proof then is easy, it's straightforward. Again, let's remember the definition, g of x minus g of y dot x minus y orthogonal over x minus y squared times omega of x omega of y dx dy. And so I just so I take the absolute value of the modulus of this x minus y per over x minus y squared. That's 1 over x minus y. So then I have a g of x minus g of y over x minus y. That's just the L infinity norm of the gradient. That's the Lipschitz constant. Oh, there's a 2 someplace. Okay, and omega are both, I don't know if I assume they're positive or not, but so let's put absolute values just in case. And so if I just integrate, and so then what do we have? R2 cross R2. No, I mean, let's say the ball of radius R over 2 complement of omega of x omega of y dx dy times this constant. And as I'm used to doing, I can write one of these as I can say put a x squared over r squared with a factor of 4. And so, so then one of these integrals will give me a second moment. And the other integral will give me the, I guess I should have been more careful. So I really wanted, let's make this be a y. And then the, so the integral with respect to y gives me the second moment. The integral with respect to x gives me the amount of vorticity outside the ball radius r. And this is multiplied by the same constant. Okay, and so if we look back here at the claim, and then there's a 1 over r squared. So we should have proved the lemma by now. right? So we have a Lipschitz constant over r squared and the Elmfine norm over r cubed, and they're both multiplied by this second moment and the amount of vorticity outside the ball radius r. And in some way, the hard work was done in the earlier lemma when we estimated the main contribution from here, which is the radial vorticity generated by the vorticity in a small ball if I'm some distance away from that small ball, the radial component of velocity. Okay, so now I think we're ready for the last lemma before the proof of the theorem. And this is what I sort of advertised at the beginning of the hour. So same assumptions above. And so this is this picture of well, here's the definition. I multiply the vorticity by a certain cutoff function, and the cutoff function looks like this. So it's going to be a function just of the modulus. In fact, I didn't write this. Oh yeah, so it's a radial symmetric function. It's a function only of the modulus, and it vanishes if the distance from the center of vorticity is less than r, and it's equal to 1 if the distance from center of vorticity is greater than r plus h. And then I assume bounds on the derivative who are compatible with that. So I think I only need the first two, but the gradient scales like 1 over h, the second like 1 over h squared with some constants. Okay, and so this is essentially the amount, again, sort of a smoothed out version of the amount of vorticity outside the scale capital R. So the way I've written it is for some reason I defined chi to be the complementary function. So chi is the function who is 1 here and vanishes there. And so then the integrand is 1 minus chi. Right, chi is 1 close to the origin and 0 away from the origin. This is chi. And this is 1 minus chi. Okay, and so I'd like to just bound the rate of growth of that quantity. And okay, that's my plan. That's what I'd like to do. And let's see if we can do it. So, okay, good. And so basically, the proof is going to be, well, we've done all the work already. We just assembled previous estimates, and I think I've collected the relevant estimates here. So we compute d u sub t dt is, and so we have a general formula for the derivative of if I multiply the vorticity by some time-dependent test function phi, we know that we'll get the integral of the vorticity against, well, d phi dt plus u dot gradient phi, plus u plus f, the background flow times gradient phi, and d phi dt. So here's phi. Phi is this quantity. D phi dt is I think everything's going to have a chi prime. We'll say the gradient of chi. And d phi dt will give us a dp epsilon dt. There's a minus sign here and there, so those cancel. And then we'll have a u plus f times the gradient. So the gradient of this function is minus the gradient of chi. So minus u minus f. Okay, that's our general formula for the derivative of an expression in this form. Okay, and so I'd like to break this into two pieces. Let's call them integral 1 and integral 2, where, okay, so integral 1 is going to contain, say, these terms, and integral 2 will contain the other term. And so I1 is equal to, and I think I put, did I do this? Yeah, so there's a 1 over, I divide by the total vorticity, therefore. Okay, and so let's see. And right, and so I have to remember what the formula was for dp epsilon dt. And well, okay, we'll do that in a second. Okay, and so remember that dp epsilon dt was, we computed this. This is one of the first things we did. And this is just the average, if you like, it's the average of the background flow, f of y t omega of y t dy over the omega. Okay, and so I'd like to just insert this into here, and we'll see what we get. And we should get something like, right. So we did this computation, and so then I1 is equal to the gradient of chi of x minus p epsilon. And then I take the dot product with f of xt minus this f of yt omega of yt over capital omega dy. And then I have a omega of xt over capital omega dx. Okay, and if we look up here, this term is exactly one of the things from our earlier lemma, the first lemma we did today. Here it is. And okay, and so here, what's the deal? Okay, so the point is, we have this gradient of chi here. Right, so I guess the point is, in this I should change variables so that I can set p epsilon equals 0. And so this is actually a ball of radius. Right, what am I doing here? Yeah, so I'm going to be a bit vague here, but I claim that, well, let's, right. Let's look at this. So in this proof, if we remember, this this x was really, it should have been, so I think I've written it as if the x omega of x dx is 0. So in the proof I said, well, this is okay, we can assume as always that the center vorticity is 0. And so that's the assumption. And so then if I didn't assume that, then I would replace this by, I think this should be a x minus p, both here and there. Okay, and again, the reason that's important is because, so what did we do in the proof? We broke our integration to a ball radius r in the complement. And on the complement, we use the fact that the second moment gives us good control. But that's only it's only if it's a ball centered at the center of vorticity. And so the relevant quantity is the distance of x from the center of vorticity. Okay, and so then once we make that observation, then this is like well, what is it? X minus p times the Lipschitz constant, and then f infinity over x minus p squared with a constant in front. And so let's see, we should then be able to right. Okay, so the point is that this is not equal to 0 only if only in this range. And so this is bounded by a constant over r squared, and this is bounded by a constant times r. We also assume that h is less than 2r. Okay, and this in fact is bounded by a constant over h. Okay, so when this all settles, we'll find that this is less than a constant over h. Let's go back to a more dignified color. A constant over h times a constant times r times the Lipschitz constant L, and then a constant over r squared, and then this m of m sub t of r, the amount of vorticity outside the ball of radius, outside the ball of radius r. I think that's what I want. Okay, so I didn't quite have time to finish this, but what's going to happen here is, okay, and so here we've used this estimate. Well, what will happen for the other terms? Well, we rewrite u using the Biot-Savart law, and so this will be an expression involving the gradient of chi, and the Biot-Savart kernel at x minus y perp over x minus y squared, omega of x, omega of y dx dy. And that's exactly the kind of expression we've estimated here. And so we're out of time, but we'll see we basically by quoting the earlier estimate at this point, we conclude with this. And so this will give us control. We'll finish on tomorrow. And I think we can finish the proof of the whole theorem. And so this will give us control over the rate of growth of essentially the vorticity outside a ball of radius r. So think of r as being a power of epsilon, epsilon to 1/2, epsilon to 1/3, something like that. You see, and I misstated this, and so I added these corrections later. These things in the numerator are all of order epsilon squared in our situation. And so if R, we can see if, and H is like the same scale, H is R over 2, for example. And so I can see if R, I can see the relevance with the square root of epsilon. If R is bigger than, if R is over square root of epsilon, then these constants, I epsilon over H squared, R squared are bounded. And if R is epsilon to a smaller power, so are these, so that would be a still larger ball, then these constants go to 0. And so, okay, so tomorrow we'll first conclude the proof of this lemma and then use it to finish the proof of both the theorem on the rate of growth of vorticity, and also I hope we can prove the whole theorem. And so the whole theorem about point vortice dynamics is an easy corollary of this bound on the rate of growth of the vorticity.